Okay, here we're going to be looking at molecules and bonds, as well as shape and chemical reactions here at Tobacco University. Now, to start off here, molecules and bonds, atoms with incomplete valence shells can share valence electrons with other atoms to form chemical bonds. Now, this transfer of electrons, is adding and removing electrons, will create an ion because electrons have a negative charge. An ionic bond is attraction between a cation and an anion as a result of electrons being transferred, as we see here, sometimes forcibly taken. Covalent bonds are the sharing of a pair of valence electrons by two atoms. However, with covalent bonds, keep in mind that there's different types because not everyone, in the case of atoms, shares equally or the same. You can see at this example of a nonpolar covalent bond because here atoms are sharing electrons equally. Everyone gets an equal share of the pizza. However, there's polar covalent bonds, and this is atoms that do not share electrons equally. This is kind of like a tug of war. One's going to kind of gain a little bit of an advantage over the other. Now, that pulling force, we call that electronegativity, and that's an atom's attraction for the electrons in a covalent bond. How strong is that electronegativity? How strong is that atom's ability to pull those electrons? See the example here with a dipole. Polar bonds creating slightly positive negative charges. Dipoles created when there's a separation between these charge concentrations. We see that with water. And that will form hydrogen bonds. And that forms when there's covalently bonded to one electronegative atom is also attracted to another electronegative atom. With the presence of hydrogen, they're kind of like little magnets that stick together. We also have van der Waals interactions, and these are interactions between molecules with close that result in some positive and negative charges. It's kind of a sticking force. That's kind of what allows this lizard to stick to the wall. Now, moving on, we're going to valence shell electron pair repulsion theory, or Vesper. This is looking at different shapes of particular molecules. Now, there's the molecular shape and function. A molecule's shape is usually very important to its function. So that's why we have to look at the shape, because that could tell us a little bit potentially about the function that it may have, just as we see as the bird's beak here able to drink. Then we have the linear form. Now, carbon dioxide is an example of a linear form, and that's just as the name implies, that's a straight line, just like these chair lifts here. Then we progress on to trigonal planar, and that's kind of looking here at one plane, but kind of that kind of triangle type effect we see with the billiard balls as well as the tomatoes here. Moving on, we have tetrahedral, and this is getting now into a little bit more of that three-dimensional pyramid-like shape to the molecule. Moving on, we have trigonal bipyramid, and that's starting to get into this diamond shape that we see here. We kind of have two pyramids on top of one another inverted. Then we have octahedral. This is kind of like the game of jacks as we see those molecules there. Now we have chemical reactions occurring. So what do we look at when we look at chemical reactions? Well, this has a lot to do with bonds and potentially the shape of those molecules. So a chemical reaction is defined as making and breaking chemical bonds. Those bonds we were just talking about, making and breaking those, we see here with the bubbles forming. That is an example of a chemical reaction. Something that takes a little bit longer is a redox reaction in this case. This is rusting of iron. Oxygen acts as the oxidizing agent and iron acts as the reducing agent. This occurs over time, and there's changes occurring at the molecular level. Another very famous redox reaction is photosynthesis, and this is a very important redox reaction. This is also another chemical reaction, falls into that same classification. Lastly, here we have chemical equilibrium is reached when the forward and reverse reactions are equal. This is kind of like players on a basketball court that might be changing or substituting. There's still the same number of players on the court, even though there might be people coming in and off the court there.